Hello, welcome back. Wherever you are tonight, and I say that with real curiosity, wondering what particular shape of room and light and quiet you found yourself in at this hour, I'm glad you're here. Maybe it's the familiar bedroom, the one your body knows without needing your eyes open. Maybe it's somewhere borrowed for the night, a couch or a guest bed that hasn't yet learnt the shape of you. Maybe you're moving, the gentle sway of a train carrying you somewhere while the rest of you has already decided to rest. Wherever it is, you're here now. That's enough. Go ahead and settle. I mean that properly. Not the half settling that's still listening for something else, but the whole thing. Let your weight become fully real against whatever is holding you up. Let your shoulders finally set down whatever they've been carrying all day. Let your breathing slow into its own rhythm, the one that doesn't need managing. You don't need to remember anything specific tonight. Some ideas will stay with you because they found something in you already waiting for them. The rest will simply pass through, and that's completely fine. This isn't a test. It's not even really information in the ordinary sense. It's more like a long, slow unspooling of something true and strange, offered at the pace of a held breath. If you're new here, welcome. This is Late Space, and what we do is take the largest ideas we can find and slow them down to the speed of a quiet evening. If you find that you'd like to come back, a gentle like or subscribe helps other people who need somewhere like this find their way here too. But that's for later, when you're more upright. For now, there's only this. Tonight, we're going to sit with something that a Nobel Prize winner said out loud, in public, in front of colleagues, that has been quietly reverberating through the scientific community ever since. Something is deeply wrong with our universe. Not wrong in the sense of broken, or dangerous, or something to be afraid of. Wrong in a much more interesting sense. Wrong the way a beautifully built house turns out to have a room nobody accounted for in the blueprints. Wrong in the sense that the map we've been using carefully, patiently, for the better part of 30 years, appears to be missing something. Something significant. Something that a person who has spent their entire career building and refining that map has now stood up and said, in effect, I don't think this map is complete. I think we may have misunderstood the universe. The person who said this is named Adam Riess. He won the Nobel Prize in Physics in 2011. And he did not win it for being wrong about things. He won it for one of the most startling, most carefully verified discoveries in the history of astronomy. The discovery that the universe's expansion, rather than slowing down under its own gravity as everyone expected, is actually speeding up. Accelerating as if you threw a ball into the air and instead of gravity gradually pulling it back down, it kept going faster and faster, up and away forever. That discovery reshaped cosmology. It gave us the concept of dark energy, the mysterious force now understood to make up the majority of everything that exists, and it earned Riess, along with 2 colleagues, the highest honour in his field. And now, more than a decade later, using an even more powerful telescope, doing even more careful work, Riess has arrived at a new and troubling conclusion. Not that his original discovery was wrong, but that the story built around it, the tidy, elegant model that cosmologists have relied on for a generation, may itself be incomplete in a way that could require, in the words of one of his colleagues, an entire textbook to be rewritten. Tonight we're going to understand exactly what he found, and why it matters, and what it might mean for absolutely everything, from the age of the universe to the shape of its far future, to the question of whether the universe might, after everything, someday reverse itself and begin, very slowly, to collapse. This is not a frightening story, it's an honest one, and there is a particular kind of peace, I think, in sitting with an honest uncertainty rather than a false certainty. Let's take our time with it. Close your eyes when you want to. Let's begin. To understand what's wrong, we first need to understand what was right. And to understand what was right, we need to go back to a night in the late 1990s when a group of astronomers working independently on two competing research teams found something in their data that none of them expected, and that very nearly none of them believed at first. The tool they were using was the exploding remnant of a dead star, specifically a particular category of stellar explosion called a Type Ia supernova. Here's what makes these explosions so useful to astronomers, and why they became, in the 1990s, the key that unlocked one of the greatest surprises in the history of science. A Type Ia supernova happens when a white dwarf star, the dense, burnt-out core of a star roughly the size of our Sun, siphons material from a companion star or merges with another white dwarf, until it accumulates just enough mass to become unstable and detonate in a runaway thermonuclear explosion. Because the physics governing this explosion is remarkably consistent from one occurrence to another, because there's a specific, well-understood mass threshold that triggers it, these explosions reach very nearly the same true brightness every single time, anywhere in the universe. This consistency makes them what astronomers call standard candles. If you know how bright something actually is, and you measure how bright it appears from Earth, the difference tells you, with reasonable confidence, how far away it must be. A standard candle held a mile away looks dimmer than the same candle held 10 feet away, in a precise, calculable way. Type I supernovae, visible clear across billions of light-years, became the most powerful distance measuring tool astronomers had ever had access to. In the mid-1990s, two separate teams, one led by Saul Perlmutter, the other including Brian Schmidt and Adam Riess, set out to use these exploding stars for a very specific purpose. They wanted to measure how the universe's expansion had changed over cosmic time. The prevailing assumption, based on everything anyone understood about gravity, was straightforward. The combined gravitational pull of all the matter in the universe should be gradually slowing the expansion down. The only real question the teams expected to answer was how much it was slowing, and whether that deceleration was strong enough to eventually stop the expansion altogether and pull everything back together in some distant future collapse. What they found instead broke that assumption completely. The distant supernovae were dimmer than they should have been, not by a small, easily dismissed margin, but by an amount that, once every conceivable source of error had been checked and rechecked, could only be explained one way: the light from those explosions had travelled farther to reach us than a decelerating universe would have allowed. The universe wasn't slowing down. It was speeding up. Its expansion was accelerating, as if some invisible hand kept pushing everything apart harder and harder, the farther out in time and space you looked. Riess later described the moment the data came together as something close to disorienting. In accounts he's given since, he's described the specific shock of that discovery, the sense of looking at numbers that simply couldn't be right, checking and rechecking them, and slowly coming to accept that the impossible result was in fact correct. It's as if you threw a baseball into the air expecting it to arc back down under gravity, and instead watched it suddenly accelerate skyward, as if some rocket had strapped itself to the ball mid-flight. Perlmutter, Schmidt, and Riess shared the 2011 Nobel Prize in Physics for this discovery, and the mysterious force behind it, whatever it was that could push the entire cosmos apart with ever-increasing strength, was given a name that has since become one of the most recognizable phrases in modern science: dark energy. Let's sit with dark energy for a moment, because understanding what it is, and, more importantly, what we don't know about it, is essential to understanding why Riess is now saying something has gone wrong. Dark energy, in the standard cosmological model that has dominated the field for the past quarter century, is generally treated as a cosmological constant. This idea traces back, in an interesting historical twist, to Albert Einstein himself. In 1917, applying his newly developed general theory of relativity to the universe as a whole, Einstein found that his equations predicted a universe that should either be expanding or contracting. It could not simply sit still. At the time, the prevailing belief among astronomers was that the universe was static, eternal, unchanging, so Einstein added an extra term to his equations, a kind of built-in repulsive force calibrated precisely to counteract gravity and hold the universe motionless. He called this term the cosmological constant. When Edwin Hubble later discovered, in the 1920s, that the universe actually was expanding, Einstein reportedly regretted ever introducing the term, sometimes described as calling it his greatest blunder. The static universe he'd been trying to preserve simply didn't exist. But in 1998, with the discovery of cosmic acceleration, Einstein's abandoned cosmological constant found new life. If you allow that constant to have a specific, small, positive value, rather than the precisely fine-tuned value Einstein originally wanted, which would have held the universe perfectly still, you get exactly the kind of gentle, persistent, ever-present repulsive push that could explain an accelerating expansion. The cosmological constant, resurrected and reinterpreted, became the leading explanation for dark energy. In this framework, the one at the heart of the standard model of cosmology, formerly called lambda CDM, where lambda represents this cosmological constant and CDM stands for cold dark matter, dark energy is treated as a fixed, unchanging property woven into the very fabric of empty space itself. It doesn't get stronger. It doesn't get weaker. It is the same today as it was 1 billion years ago, and the same as it will be 1 billion years from now. A permanent, constant feature of the universe, quietly pushing everything apart forever at exactly the same intensity. This simple picture, dark energy as an eternal constant, has been remarkably successful. It fits an enormous range of observations. It correctly predicts in broad strokes the age of the universe, the large-scale distribution of galaxies, and the pattern of the cosmic microwave background, that faint, ancient glow of light left over from the earliest moments after the Big Bang. Dark energy, under this model, currently makes up roughly 68% of everything that exists in the universe. Not 68% of the matter, 68% of the total energy content of the entire cosmos. It is, by a wide margin, the single largest component of reality as we currently understand it. And we don't know what it is. This is worth sitting with, because it's easy to let a percentage like that slide past without feeling its full weight. The majority, the outright majority, of everything that exists in the observable universe is something we cannot directly detect, cannot touch, cannot examine in a laboratory, and can currently describe only by the effect it has on the expansion of space itself. We have given it a name. We have measured its strength. We have built an entire cosmological model around the assumption that it behaves in one particular simple way. And now, according to Adam Riess and a growing number of his colleagues, there is real, mounting evidence that this assumption might be wrong. Wherever you are, I hope you're comfortable. Let's breathe here for a moment, because we're about to move from the well-established story of dark energy's discovery into the far more uncertain, far more recent territory of what might be wrong with it, and this next part deserves to be approached slowly, carefully, the way you'd approach any genuinely open question. The instrument at the centre of this new uncertainty is called DESI, the Dark Energy Spectroscopic Instrument. DESI sits mounted on the Nicholas U. Mile telescope at Kitt Peak National Observatory on a mountaintop in the Arizona desert. It is an extraordinary piece of engineering, 5,000 individually controlled robotic optical fibres, each one capable of being precisely aimed, under computer guidance, at a different distant galaxy, capturing the full spectrum of light that galaxy emits. In a single night, DESI can gather detailed spectra from tens of thousands of galaxies. Over the course of its ongoing survey, it has been building the largest, most detailed three-dimensional map of the universe ever constructed, plotting the positions of tens of millions of galaxies and quasars across billions of years of cosmic history, from the relatively nearby universe we see today, all the way back to a time when the cosmos was only a small fraction of its current age. The specific feature DESI is designed to measure is called baryon acoustic oscillation, a subtle, preserved pattern in the distribution of galaxies that originated as literal sound waves rippling through the hot, dense plasma of the very early universe. Sound waves that froze in place once the universe cooled enough for atoms to form, leaving behind a kind of fossilized ruler embedded in the large-scale structure of the cosmos. By measuring the apparent size of this ruler at many different points across cosmic history, DESI can trace with remarkable precision exactly how the universe's expansion rate has changed over billions of years. In April 2024, the DESI collaboration, bringing together more than 70 research institutions worldwide, released its first year of results. And embedded within that enormous dataset was a hint. Not a certainty, a hint. The data seemed to suggest that dark energy, rather than behaving as a perfectly constant, unchanging force the way the standard model assumes, might actually have been somewhat stronger in the distant past than it is now. As if over billions of years dark energy's push had gradually been losing some of its strength. The scientific community responded with the appropriate mixture of intrigue and caution that any single, not yet definitive result deserves. A hint is not a discovery. Extraordinary claims, as the saying goes, require extraordinary evidence, and 1 year of data, however impressive the instrument gathering it, was not yet extraordinary enough to overturn 25 years of an otherwise successful model. Then, in March 2025, DESI released its second year of data. And the hint didn't go away. It got stronger. Let me describe as precisely and honestly as I can what this second release actually showed, because the specifics matter, and because I want to give you the real texture of what scientists were looking at, rather than a simplified or sensationalized version. The DESI team, now working with a substantially larger and more precise dataset, found that when they combined their baryon acoustic oscillation measurements with independent data from distant supernovae, including newer, more carefully calibrated supernova catalogues than were available even a year earlier, the preference for evolving dark energy, rather than a perfectly constant one, grew more statistically significant. In the most robust combinations of datasets, the deviation from a simple, unchanging cosmological constant reached a confidence level that professional cosmologists describe using a unit called sigma, where higher numbers indicate a smaller likelihood that what's being observed is simply random statistical noise. The results hovered in a range. Different combinations of data produce slightly different numbers, generally somewhere between roughly 2.5 and 4 sigma, depending on exactly which datasets were combined and how. In particle physics, the traditional threshold for claiming a definitive discovery is 5 sigma, representing odds of roughly 1 in 3.5 million that the result is simply a statistical fluke. DESI's evidence for evolving dark energy, while significant and while it strengthened meaningfully between the first and second years of data, has not yet crossed that 5 sigma threshold. This is an important and honest caveat, and it's one that essentially every serious researcher discussing these results, including Riess himself, has been careful to include. This is not, as of the most recent data, a confirmed 5 sigma textbook rewriting discovery. It remains what scientists sometimes call an intriguing tension, a persistent, reproducible signal that keeps showing up. That keeps getting stronger as more and better data arrives, but that has not yet crossed the threshold required for the field to declare it definitively settled. But here is what makes it different from countless other minor statistical curiosities that appear and then quietly fade in astronomical data. It is consistent. It appeared in the first year of DESI data. It reappeared, strengthened, in the second year. It has been checked against multiple different independently calibrated supernova catalogues, and the general pattern, dark energy appearing weaker today than it was in the more distant cosmic past, keeps showing up, even as the specific statistical strength shifts slightly depending on exactly which combination of data you examine. Alexei Lotord-Harnett, a spokesperson for the DESI collaboration, described the moment plainly. What we are seeing is deeply intriguing. It is exciting to think that we may be on the cusp of a major discovery about dark energy and the fundamental nature of our universe. And it was in discussing exactly these results, this specific, still developing, not yet fully confirmed but persistently strengthening signal, that Adam Riess made the comments that have since travelled widely through the scientific and popular science communities. Discussing the DESI findings, Riess noted that dark energy appeared to have lost its kick several billion years ago. He was careful, characteristically, to add an important caveat: this finding is not settled science. But he went on to say that if it does hold up under further scrutiny, it would require nothing less than a wholesale revision of the standard model of cosmology. A colleague of his, Colin Hill, a cosmologist at Columbia University, put it even more starkly in a comment that has since been widely quoted: if this result holds, the textbooks he currently uses in his own classroom would need to be rewritten. I want to pause here and make sure we hold this properly, because I think it's easy, especially at this hour, in the quiet, to let a phrase like the textbooks would need to be rewritten slide past as simple dramatic flourish. It isn't. It's an extraordinarily weighty thing for a working cosmologist to say about their own field, and I want you to feel the actual size of what it would mean. The standard model of cosmology, lambda CDM, is not a minor or provisional framework. It is the result of decades of painstaking, cross-checked, independently verified work by thousands of scientists across the world. It correctly predicts, with extraordinary precision, the pattern of the cosmic microwave background, that faint afterglow of the Big Bang, mapped in exquisite detail by the European Space Agency's Planck satellite. It correctly predicts the relative abundances of hydrogen, helium and lithium that were forged in the first few minutes after the Big Bang. It correctly predicts, in broad strokes, how galaxies and galaxy clusters are distributed throughout the observable universe. This model has been tested, and tested again, and tested from a dozen independent angles, and it has passed nearly every one of those tests with a level of precision that is, frankly, one of the great triumphs of the human scientific enterprise. For a working cosmologist, someone whose entire career has been built on the reliability of this framework, who teaches its equations to students every semester, who has watched it succeed test after test after test, to say that the textbooks might need to be rewritten is not casual. It is the kind of statement that only gets made when the evidence has become genuinely difficult to explain away. And it isn't just the DESI dark energy hint, standing alone, that has brought cosmology to this point. It's that this hint has arrived alongside several other independent, equally puzzling anomalies, discovered through entirely different methods, using entirely different instruments that all seem to be pointing from different directions. At the same underlying conclusion, something about our current model of the universe is incomplete. Let me walk you through the second of these anomalies, because it's the one most directly tied to Adam Riess's own decades of work, and it's the one that gives his recent comments about dark energy so much additional weight. It's called the Hubble tension, and it concerns a single number, the rate at which the universe is currently expanding. This number, called the Hubble constant, can be measured in two entirely independent ways. The first method, the one Riess himself has spent much of his career refining, builds what astronomers call a cosmic distance ladder. It starts by measuring the distances to relatively nearby stars using pure geometry, then extends that measurement outward using a special class of pulsating stars called Cepheid variables, whose brightness is directly tied to how quickly they pulse, and then extends outward further still using those same Type 1a supernovae that first revealed cosmic acceleration back in the 1990s. Following this ladder rung by rung all the way out to distant galaxies, and comparing their distances to how quickly they're receding from us gives a direct present-day measurement of the universe's expansion rate. The second method takes a completely different approach. It uses the cosmic microwave background, that ancient light from 380,000 years after the Big Bang, mapped in extraordinary detail by the Planck satellite, and by fitting the standard cosmological model to the precise pattern of temperature variations within it, predicts what the expansion rate should be today, extrapolating forward from the conditions of the very early universe. For years, these two methods produced numbers that didn't quite agree, and for years, the leading suspicion among cosmologists was that this disagreement stemmed from some hidden, uncorrected measurement error, most likely some subtle bias affecting the distant galaxy measurements, perhaps caused by nearby stars in crowded galactic fields blending together in ways that made distances appear artificially different than they actually were. This is precisely the suspicion that the James Webb Space Telescope was uniquely positioned to test. With a mirror nearly 3 times larger than Hubble's and far superior resolving power in infrared light, Webb could distinguish individual stars in distant galaxies with a clarity Hubble simply couldn't match. Riess and his team used this capability directly, observing the very same Cepheid variable stars in the very same distant galaxies that had produced the original discrepancy, checking specifically for the kind of stellar crowding that might have been inflating the measurements. Webb found no such crowding. The measurements matched Hubble's earlier results almost exactly. The suspected error simply wasn't there. The conclusion Riess drew from this, in the paper that followed, has since become one of the most quoted lines in recent cosmology. With measurement errors negated, what remains is the real and exciting possibility we have misunderstood the universe. This sentence, said by someone who has spent the better part of 2 decades trying to find the mistake, trying to explain the discrepancy away through ordinary, mundane measurement error, and coming up empty every single time, carries an entirely different weight than the same sentence said by anyone else. Wherever you are, I hope you're still comfortable. We're building something significant here, piece by piece, and I want to make sure it has time to settle properly before we go further. So here is the shape of the puzzle, as it currently stands. 2 of the most precise, most carefully verified measurements of the universe's expansion rate, one built from the nearby present-day universe, the other extrapolated forward from the ancient cosmic microwave background, disagree with each other by an amount too large, too consistent, and too thoroughly checked to be explained by ordinary measurement error. This is the Hubble tension, and it has now been confirmed, not resolved, by the very telescope that many hoped would put it to rest, and separately, but almost simultaneously, an entirely different instrument, using an entirely different method, mapping the 3-dimensional positions of tens of millions of galaxies across billions of years of cosmic history, has found a persistent, strengthening signal suggesting that dark energy, the mysterious force responsible for the universe's accelerating expansion, might not be the fixed eternal constant the standard model assumes. It might instead be evolving, weakening specifically in more recent cosmic time compared to its strength billions of years ago. These 2 puzzles are not identical. They come from different observations, use different instruments, and involve different aspects of cosmic history. But they share a deep structural connection, because both of them ultimately trace back to the same underlying question. Does our simple, elegant 25-year-old model of dark energy, the assumption that it is a single, unchanging constant, woven permanently into the fabric of space, actually capture the full truth of what's driving the universe's expansion? If dark energy has genuinely been changing over cosmic time, weakening, as the DESI data hints, this could, in principle, help explain the Hubble tension as well. A universe in which dark energy's strength shifts over billions of years would have a different, more complicated expansion history than the standard model assumes. and a more complicated expansion history could plausibly account for why measurements of the expansion rate taken from the ancient early universe don't quite match measurements taken from the nearby present-day universe. This is not yet confirmed. I want to be honest and careful about that, the way Riess himself has been careful. But it is exactly the kind of connection that makes physicists sit up and pay attention. Two independent anomalies discovered by two entirely different research programs that might, if the evidence continues to strengthen, turn out to be two different windows onto the exact same missing piece of physics. And there is a third thread in this story, one we've touched on in earlier conversations here on Late Space, but that deserves to be woven back in tonight, because it adds yet another independent voice to this chorus of anomalies, and because it comes directly from the very telescope whose confirmation of the Hubble tension helped set this whole conversation in motion. It concerns the earliest galaxies the universe has ever produced, when the James Webb Space Telescope turned its extraordinary infrared vision toward the deepest reaches of cosmic history, toward galaxies whose light has been travelling toward us for well over 13 billion years, since a time when the universe itself was less than 1 billion years old. It found something the standard model of galaxy formation did not predict. According to that standard model, the earliest galaxies should have been small. Chaotic, actively forming, but not yet mature irregular clumps of gas and young stars, still in the earliest, messier stages of gravitational assembly, having had only a few 100 million years, at most, to gather themselves together out of the smooth, largely featureless material of the infant universe. Instead, Webb found galaxies that were in some cases startlingly large, startlingly massive, and startlingly organised, including, in one particularly striking 2025 discovery, a fully formed spiral galaxy, complete with defined rotating arms, existing when the universe was only about 1.5 billion years old. Organised spiral structure of that kind is something astronomers generally expect to take many billions of years of relatively calm, undisturbed development to produce, not something that should exist in the universe's rowdy, violent, still-forming infancy. Other early galaxies discovered by Webb appear to contain far more mass in stars than the standard model of galaxy formation allows for, given the extremely limited amount of time available since the Big Bang for that material to have assembled and ignited. In some of the most extreme cases, the inferred efficiency of star formation required to explain what Webb is seeing pushes right up against, or in a few disputed cases even beyond, the theoretical limits that current physics considers possible. None of this, on its own, definitively overturns the standard cosmological model. Some of the most extreme early estimates have already been revised downward, as astronomers accounted for contaminating light from actively feeding supermassive black holes at the centres of some of these galaxies, and as more detailed follow-up observations have refined the original estimates. This is exactly how science is supposed to work. Extraordinary claims get checked, rechecked, and adjusted as better data arrives. But what has not gone away, even after all of that careful rechecking, is a persistent population-level pattern. The early universe, taken as a whole, appears to be more massive, more structured, and more rapidly assembled than the standard model comfortably predicts. 3 independent threads, then, the Hubble tension, now confirmed rather than explained away. The DESI hint of evolving dark energy, strengthened rather than weakened by a second year of data. And Webb's population of unexpectedly massive, unexpectedly organised early galaxies. 3 separate observational programs using 3 entirely different instruments and 3 entirely different methods, all converging on the same uncomfortable conclusion: the standard model, for all its genuine and hard-won successes, appears to be missing something. Let me tell you what Adam Riess said, specifically about what might come next, because this is where his comments move from simply identifying a problem to genuinely grappling with what it might mean for the deep future of everything. If dark energy really has been weakening over cosmic time, if the DESI hint continues to strengthen as more data arrives, eventually crossing that 5 sigma threshold and becoming a confirmed discovery rather than an intriguing tension, then one of the most fundamental assumptions underlying our entire picture of the universe's ultimate fate would need to be reconsidered. For the past 25 years, the standard textbook picture of the universe's distant future has generally assumed that dark energy, as a fixed, unchanging cosmological constant, will simply continue doing exactly what it's doing now, forever. Under this assumption, the universe expands and cools indefinitely into an ever colder, ever darker, ever more diffuse future, a scenario cosmologists sometimes call the heat death of the universe, in which, over spans of time far longer than anything we've discussed in previous episodes here, every star eventually burns out, every black hole eventually evaporates, and the universe settles into a permanent, featureless, maximally spread out state of near total emptiness and cold. But if dark energy is not in fact a fixed constant, if it can weaken over time, as the current DESI data hints, then a startling range of alternative futures suddenly becomes possible, at least in principle. Riess himself, in discussing these implications, has noted that dark energy could, hypothetically, continue weakening all the way down to zero, and then, more startling still, potentially continue past zero into negative territory, becoming, in effect, an attractive force rather than a repulsive one. If that happened, and I want to stress clearly and honestly that this remains deeply speculative, resting on data that has not yet reached the confidence threshold required for a confirmed discovery, the ultimate implications for the universe's fate would be dramatically different from the standard heat-death scenario. The dark energy that turns negative, becoming attractive rather than repulsive, could in principle eventually halt the universe's expansion altogether and then reverse it. Rather than expanding forever into cold, dark, diffuse emptiness, the universe could instead begin, at some point in the far future, to contract, galaxies drawing back together, the cosmic microwave background reheating as everything compresses, moving not toward a permanent quiet heat death, but toward its opposite, a catastrophic fiery collapse that cosmologists have given a suitably dramatic name, the Big Crunch. Riess's own summary of this uncertainty, as reported from his public discussions of these results, was direct and, I think, genuinely honest in a way that I find rather beautiful, whether the future holds an endless cold expansion, or a distant fiery collapse, or something else entirely that current models haven't even properly considered yet. The deep future of the universe is wide open. Wherever you are, I hope you're still comfortable. I want to sit with that phrase for a while, because I think it deserves more than a passing mention. The deep future of the universe is wide open. For a generation, cosmology has operated with a reasonably settled, if sombre, picture of how everything eventually ends. An eternal, ever colder, ever emptier expansion, stretching forward into a future so distant it barely deserves to be called a future at all. More a kind of permanent, static, featureless silence. We built entire episodes here at Late Space around exactly that picture, the slow fading of the last stars, the eventual evaporation of the last black holes, the long, patient dissolution of everything into cold, diffuse nothing. And now, one of the very people whose own discoveries helped establish that picture in the first place is standing in front of colleagues and saying, carefully, honestly, without exaggeration, we might have gotten this wrong. Not wrong in the sense of the accelerating expansion being false, that discovery, confirmed independently many times over in the 25 years since, is not in doubt, but wrong in the sense that the specific character of that acceleration, whether it is truly permanent, truly unchanging, truly a fixed and eternal feature of reality, may not be settled after all. I find something genuinely moving in that admission, and I want to try to articulate why, because I think it says something important about what good science actually looks like, especially at an hour like this, when the temptation is often to want firm, comforting answers rather than open, honest questions. It would have been easy, in a certain sense, for Riess to simply defend the model he helped build. He is, after all, one of the primary architects of our modern understanding of dark energy. His name is permanently, gloriously attached to one of the most significant discoveries in the history of physics. There would be nothing unusual, nothing even particularly dishonest, in a scientist quietly downplaying inconvenient new data that complicates a picture they themselves helped establish. That is not what happened. Instead, Riess looked at the new evidence that, if it holds up, complicates and possibly overturns significant parts of his own earlier work, and said plainly that this is exciting, that this is exactly the kind of result a scientist should hope for. Not because being wrong is pleasant, but because discovering that you were incomplete, that there is more to learn, that the universe still has secrets left to reveal, is, in the deepest sense, the entire point of the enterprise. I want to take a slightly different path now and talk about what it actually feels like, from the inside, to be a scientist at a moment like this, because I think there's something valuable in trying to inhabit that particular experience for a while, here, in the quiet, before we continue. Imagine spending years, decades in Riess's case, building a career around a specific, hard-won understanding of how the universe works. Imagine the painstaking effort involved, the careful calibration of instruments, the endless cross-checking of results, the years spent ruling out every possible source of error before you're willing to publish even a single carefully hedged claim. Imagine finally arriving at a result so significant that it reshapes your entire field, earning you the highest honour your profession can bestow. And then imagine, more than a decade later, using an even better instrument, doing even more careful work, finding a new signal in the data, one that doesn't confirm your earlier picture, but complicates it, one that suggests the elegant, simple story you helped tell may be missing an important chapter. There are, broadly, two ways a person could respond to that moment. One is defensiveness, protecting the established narrative, minimizing the new anomaly, waiting quietly for it to resolve itself or fade away, as many statistical curiosities eventually do. The other is curiosity, genuine, open, slightly unsettled curiosity, the kind that says, "This is strange, and I don't yet understand it, and that is far more interesting than being comfortably certain." Everything in Riess's public comments about these results, the careful caveats, the repeated acknowledgement that this remains unsettled, unconfirmed, requiring further verification, alongside the genuine excitement in his voice about what it might mean if it does hold up, suggests someone who has chosen curiosity, someone who is more interested in what's actually true than in preserving the tidiness of a picture he helped build. I think this is one of the most beautiful things about science, when it's practiced well, and I think it's worth sitting with at this hour, in this particular quiet. The willingness to say publicly in front of your peers about your own field, about work you yourself helped establish, "I think we might have gotten this wrong," and I find that exciting rather than threatening. That is a genuinely rare and valuable form of intellectual honesty. It's not the kind of thing that gets rewarded by certainty or comfort. It gets rewarded, eventually, by understanding something true, even if that truth turns out to be stranger and more complicated than the story you started with. Let me bring this back now to the specific physics, because I want to make sure we understand, as clearly as tonight's pace allows, exactly what kind of wrong we're talking about. Because I think it's easy, especially with a title as dramatic as the one we started with tonight, to imagine something more catastrophic than what's actually being proposed. Nobody in this conversation, not Riess, not the DESI collaboration, not the researchers studying Webb's early galaxies, is suggesting that the Big Bang didn't happen, or that the universe isn't expanding, or that dark energy doesn't exist at all. Those foundational pillars of modern cosmology remain about as solid as any result in observational science. What is being questioned, specifically and carefully, is a much narrower but still deeply important assumption: whether dark energy behaves as a perfectly simple, perfectly constant, perfectly unchanging property of space, the way Einstein's resurrected cosmological constant assumes, or whether it is something more dynamic, something that can change in strength over cosmic time, something with its own internal physics, its own evolution, its own story, rather than simply being a fixed number bolted permanently onto our equations. If dark energy is dynamic rather than constant, this would represent a genuinely significant revision to the standard model, significant enough to justify Colin Hill's comment about rewriting textbooks, significant enough to justify Riess's comment about the deep future being wide open. But it would not mean that everything we currently understand about the universe is false. It would mean, instead, that our picture is incomplete in a specific, identifiable, scientifically productive way. The same way that Newton's physics wasn't wrong, exactly, but incomplete, later extended and refined by Einstein's relativity in ways that revealed new physics operating at extreme speeds and enormous masses that Newton simply never had reason to consider. This is, I think, the single most important thing to hold on to tonight, at this hour, as we sit with the idea that something is deeply wrong with our universe. The wrongness being discussed here is not chaos. It's not the collapse of scientific understanding. It is instead the very specific, very productive, very exciting discovery that our best current model, however successful, has a gap in it. A gap that new instruments, better data, and more careful thinking are actively working to fill, right now, in research papers being written and debated as you lie here listening to this. Wherever you are, I hope you're comfortable. Let's widen our view for a moment and talk about what comes next, because this story, unlike so many of the ones we tell here at Late Space, is genuinely actively unfolding in real time, and I think it's worth understanding what the coming years are likely to bring. The DESI collaboration continues its survey, and each additional year of data adds more galaxies, more precision, more statistical power to the question of whether dark energy is truly evolving. If the current trend holds, if the signal keeps strengthening the way it strengthened between the first and second data releases, the field may well cross that critical 5 sigma threshold within the next few years, transforming an intriguing tension into a confirmed discovery. Alongside DESI, the European Space Agency's Euclid satellite, launched in 2023, is conducting its own independent survey of the universe's large-scale structure using different methods and different systematic uncertainties, providing exactly the kind of independent cross-check that any genuinely revolutionary claim requires before the broader scientific community will fully accept it. If Euclid's data, gathered through an entirely separate observational approach, points toward the same conclusion as DESI's, that convergence would represent a substantial strengthening of the case for evolving dark energy. Meanwhile, the James Webb Space Telescope continues its observations of the early universe, continuing to build out the population of unexpectedly massive, unexpectedly organized early galaxies, and continuing to test, refine, and occasionally revise its most extreme early findings as more detailed follow-up data arrives. And ground-based and space-based instruments continue refining the measurements underlying the Hubble tension itself, looking for any remaining subtle source of systematic error that might yet explain the discrepancy, while so far consistently failing to find one. This is, in other words, not a settled story that concluded the moment Riess made his comments. It is an actively unfolding scientific investigation, playing out in something close to real time, with new data arriving regularly, existing claims being tested and retested, and the broader picture becoming gradually more clear, even as that clarity, for now, points toward genuine uncertainty rather than a comfortable resolution. I want to tell you something about what this kind of moment has historically meant for physics, because I think it offers a useful, steadying perspective, especially at this hour, when uncertainty can sometimes feel unsettling rather than exciting. The history of physics is punctuated again and again by exactly this kind of crisis, a well-established, thoroughly tested model suddenly confronted by new data it cannot fully explain, forcing the field to either find some previously overlooked error or else genuinely extend and revise its understanding of reality. At the end of the 19th century, physicists largely believed they had essentially finished the project of understanding the physical universe, that only a few small details remained to be worked out. And then came a handful of stubborn, persistent anomalies, the strange behaviour of light in the famous Michelson-Morley experiment, the puzzling spectrum of light emitted by hot objects, tiny unexplained wobbles in the orbit of Mercury. Each of these anomalies seemed individually like a minor curiosity, the kind of small, nagging discrepancy that might eventually be explained away by some overlooked measurement error. Instead, they turned out to be the first cracks revealing an entirely new layer of physics beneath the surface of the old one. Einstein's special and general relativity emerged, in significant part, from taking these small anomalies seriously rather than dismissing them. Quantum mechanics emerged from taking the strange behaviour of light and heat seriously rather than assuming it must eventually resolve itself within the existing framework. The physics that emerged from that period of crisis and uncertainty didn't discard everything that came before it. Newton's equations still work extraordinarily well for everyday speeds and everyday masses. It extended that earlier understanding, revealing that it had been all along a special case of something larger, richer and stranger. We may well be living through an early chapter of a similar story right now. The Hubble tension, the evolving dark energy hint, the unexpectedly massive early galaxies. Each one individually might eventually be explained away by some subtle, currently unrecognized source of error. Or, taken together, they might be the first visible cracks in a model that has served remarkably well for 25 years, revealing that it, too, was a special case, correct as far as it went, but incomplete, waiting for someone to discover the larger, stranger physics operating just beneath its surface. We don't know yet which of these it will turn out to be, and I think that not knowing, held properly, held gently, held with the same curious openness that Riess himself seems to be modelling in how he talks about these results, is one of the more genuinely exciting positions a person can occupy, scientifically speaking. Let me offer you something now that moves a little further from the specific physics and closer to the feeling underneath all of this, because I think that feeling is, in its own way, the real destination of tonight's conversation. There is a particular kind of comfort that comes from certainty, from having a complete settled picture of how things work, filed away and closed, no longer requiring your attention or your wonder. And there is a different, quieter, perhaps more mature kind of comfort that comes from sitting with genuine, honest uncertainty. Not the anxious uncertainty of not knowing something you desperately need to know right now, but the spacious, patient uncertainty of watching a genuinely open question slowly, carefully, collaboratively resolve itself over years through the accumulated work of thousands of careful people. Adam Riess, standing in front of his colleagues and saying that we may have misunderstood the universe, is not describing a crisis in the alarming sense of that word. He is describing an invitation for the next generation of instruments, the next generation of researchers, the next years of careful, patient data collection to reveal something that the current generation of tools simply wasn't yet capable of seeing clearly. There's something in that, I think, worth carrying with you into sleep tonight. The universe, it turns out, is not obligated to conform to the tidiest possible story we've told about it. It is vast enough, old enough, strange enough, that even our most successful, most carefully verified models eventually run up against something they cannot fully explain. And rather than being a source of despair, this seems again and again throughout the history of physics to be the exact mechanism by which understanding actually deepens, not through comfortable confirmation of what we already believed, through the humbling, occasionally unsettling, ultimately clarifying experience of discovering we were missing something. Let's come back, one more time, to the specific words that started tonight's conversation, because I want to make sure we leave them properly understood, rather than simply repeated as an attention-grabbing headline. Something is deeply wrong with our universe. What this actually means, once you've sat with the full context, is something considerably more precise and considerably more hopeful than the phrase alone might suggest. It means our best current model of dark energy, the mysterious force responsible for the majority of everything that exists, the force driving the accelerating expansion that Riess himself first discovered, appears, based on multiple independent lines of increasingly strong evidence, to be an incomplete description of something more complex and more dynamic than a simple, unchanging constant. It means that the standard, decades-old picture of the universe's ultimate fate, an endless, cold, ever-expanding future, while still entirely possible, is no longer the only serious option on the table. The deep future, in Riess's own careful words, is wide open. It means that some of the most careful, most decorated, most rigorously trained scientists currently working are looking directly at their own most successful theories and saying, honestly, in public, we may need to revise this. And it means, I think most importantly of all, that the project of understanding the universe, the project this whole channel exists to gently walk you through, night after night, one quiet idea at a time, is nowhere near finished. There is more to learn. There are genuine, active, unresolved mysteries being investigated right now by real people, using real instruments, following real data wherever it honestly leads them. Even when that means questioning conclusions they themselves once helped establish, that is not something to fear. It is, I think, one of the more beautiful things happening in science today. Let's come down now, slowly, gently, the way we always do, toward the end of tonight's long conversation. Here is what is true, as carefully and honestly as I can leave it with you. 25 years ago, astronomers led by Adam Riess and his colleagues discovered that the universe's expansion is accelerating, driven by a mysterious force we call dark energy, a discovery so significant it earned the Nobel Prize in Physics. The standard model built around this discovery has assumed, for a quarter century, that dark energy behaves as a simple, permanent, unchanging constant. New evidence, gathered by the James Webb Space Telescope and by the Dark Energy Spectroscopic Instrument, suggests this assumption may be incomplete. Webb has confirmed, beyond reasonable doubt, that there is a genuine discrepancy in how fast the universe is expanding, depending on which method you use to measure it, a discrepancy that cannot be explained away by measurement error. And DESI has found a persistent strengthening signal suggesting that dark energy itself may have been weakening over billions of years of cosmic history, rather than remaining perfectly constant. Neither finding has yet crossed the threshold required to be called a fully confirmed discovery. Both remain, honestly and carefully, open questions, genuinely uncertain, actively being investigated. Not yet settled. And Adam Riess, one of the people most responsible for our modern understanding of dark energy, has looked at this evidence and said plainly that we may have misunderstood the universe, that the deep future of everything, whether it ends in cold, eternal expansion or distant fiery collapse, or something else entirely that current models haven't yet properly considered, remains. For now, genuinely, honestly, wide open. This is not a frightening thing to fall asleep with tonight. It is, I think, a genuinely beautiful one. You are alive during a moment when some of the most careful, most rigorously trained minds our species has ever produced are looking honestly at the universe, admitting what they don't yet understand, and setting out, patiently, collaboratively, to understand it better. Close your eyes if they're not already closed. Somewhere in the Arizona desert, on a quiet mountaintop, 5,000 small robotic fibers are patiently gathering light from tens of millions of distant galaxies, slowly building the largest map of the universe ever constructed. Somewhere in orbit, 1.5 million kilometers from Earth, a golden mirror is turning gently, gathering light that has travelled for over 13 billion years from galaxies whose existence still doesn't quite fit our best models of how the early universe was supposed to behave. And somewhere, in an office or a laboratory, a scientist who once discovered that the universe was accelerating is now looking at new data suggesting that even that discovery, Nobel Prize and all, might be part of a larger, stranger, not yet fully understood story. That is not an ending, it's an opening. The universe is not finished revealing itself to us, and the honest, careful, patient people working to understand it are not finished asking the right questions. Thank you for spending tonight here. Thank you for sitting with genuine uncertainty instead of needing it resolved before you could rest. Thank you for letting the universe be as strange as unfinished and as quietly wonderful as it actually is. Sleep well, and somewhere out there, the data keeps arriving. The map keeps growing. The question stays open. Good night.